session, but because of some unfortunate circumstances, it had to be deferred. Now, I what I am going to do is um, we'll talk about the satellite launch vehicles, but more than that, I'm going to talk about the preliminary work which goes into launching. That is how the whole thing starts and how it progresses, and in various work centers, and how it reaches the launch pad and then gets launched from there. What all goes behind that? So that's the basic uh, method which I'm going to follow today. Now, uh, before the launch, because the launch actually takes place, a lot of preliminary work needs to be carried out. This is like you have to definition. You have to work out mission definition, and then based on the definition only and the work done by the various work centers, the shape of the satellite and the launch vehicle uh, begins to emerge. And then once the mission definition is completed, then the work center will go about making their sub-assemblies and everything. And these could be mechanical, electrical, electronic, structural, and also software. And this work could take anything between 6 months to 24 months, depending on how complex or how new the mission definition is. So let me begin. So first thing which is we define the satellite, the application of the satellite. That is, you have a satellite, but what is it going to do? What is the basic idea behind launching it? Why? Um, for example, when the Prime Minister goes to Sri Harikota and says that, okay, you make a satellite for SARC countries. That's fine. But then what is the satellite going to do? Is it going to do, what are the needs of those SARC countries? Is it going to be only telecommunication, or is it remote sensing, or that's for this, but otherwise, in satellite could be used for interplanetary mission, like going to Moon or Mars or Venus or something like that. Or it could be astronomy, that is, it has a telescope like the James Webb Space Telescope, which has gone up recently. Or it could be a human in space, which, of course, Gaganyaan, which is about to be launched within a year or so. So first, once satellite application is defined, then we come to the next level. That is, what is the orbit? What's going to be the orbit in which the satellite is going to be placed? Is it going to be polar sun-synchronous, or is it going to be geosynchronous for a communication satellite, or is it going to be the low Earth orbit, or is it going to be Hoffman transfer? Hoffman transfer means when it leaves the Earth's orbit and goes into some other planet's orbit. Like it can go from Earth, it can go to the moon's orbit, or it can go to Mars. Going to Mars is not straightforward. It, from the Earth, it leaves the Earth's orbit, goes into a solar orbit, just like any of the other planets, and then then it is captured by the moon, and then Mars, and then it is captured by Mars and goes into Mars orbit. So that is called a Hoffman transfer. Once you have defined the orbit, then uh, you you define the location of the satellite in orbit, that where exactly it's going to be placed in orbit around the Earth. The next thing which comes is the instrumentation which is required for the satellite. That again depends on what we are asking the satellite to do. That if it's going to be remote sensing, it should have some cameras, it should have some infrared cameras, it should have some instrumentation for capturing the data, sending the data down, antennas, all those things are there. So all that instrumentation is planned. And the expected life. Now, the life of a satellite, as you know, depends largely on the amount of propellant it carries. So, if the life is 5 years, it carries a certain amount of propellant. If its life is more than five, let's say 7 or 10 years, the propellant is going to be much more than that. So, That's how the weight of the satellite is going to be defined. Weight and size, dimensions. So once the this is finalized, then you think of the launch vehicle which is going to be used for launching this satellite. Is going to be PSLV. Um, I'll come to that slightly later, but PSLV can launch about maximum 1,800 kilograms. GSLV can launch about 2,500 kilograms. I'm talking of um, a in polar orbit, or in case of GSLV, it's going to be a geosynchronous orbit, transfer orbit, or a Mark III launch vehicle, which can take about 4,000 kilograms. So once that is defined, then you have to to look at the flight profile which will be used for reaching the desired orbit. Now, for example, if it's going to be launched from Sriharikota, and if it's going to be into a geosynchronous transfer orbit, it has to go around equator. So that is how you have to define the flight profile for that. How exactly is going to reach the equator? If it's going to be a polar, then it has to go southwards. And it cannot go straight southwards only, because then the huge mass of Sri Lanka comes in between. So it has to divert. So I mean, what I mean is that the flight profile has to be defined to achieve the required orbit. And once you define that, then you have the guidance law, which will decide actually where exactly you make a turn, how to make a turn, how to reach that desired orbit. And then the last thing is the specific requirements for ground stations, telemetry, checkout, launch pad, and also the requirements for ultimate usage of the satellite. That is, how it's going to be used by the users. I mean, what sort of data, how the data is going to be acquired, how it's going to be used. So that's the basic idea. So once all these things are defined, then we are ready for starting the work for the work in the work centers to start developing the the sub assemblies for the satellite and for the launch vehicle. Now there are the launch vehicles which are used in the Indian space program. There are, as we all know, there are currently three launch vehicles which are being used at present in the Indian space program. PSLV, which is the workhorse of the Indian space program. We have launched it about 52 times. 52nd launch came very recently, last week actually. Uh, and it can lift 1,700 kilograms into a polar orbit or 700 kilometers altitude and a polar north to south orbit. Or you can have GSLV Mark II, which can lift 2,500 kg to geosynchronous transfer orbit. That is something like 180 into 36,000 kilometers orbit. Mark III, GSLV Mark III, which is known as LVM3, Launch Vehicle Mark III, which can lift 4,000 kg to GTO or 10,000 kg to a low Earth orbit. And this is what is going to be used for our Gaganyaan mission. There are two more launch vehicles which are still in the pipeline, which are on the drawing board, which are being worked out. These are called SSL, that is small scale satellite launch vehicle, which can lift a 600 kg payload to low Earth orbit or 300 to sun synchronous polar orbit, which is about 700 kilometers high. Or a unified launch vehicle, which can be configured to anything between to launch anything from 4,500 kg to 40,000 kg, all the way to geosynchronous transfer orbit, and it can have many other applications and uses also. So now we'll just have a brief view of the launch vehicles. This is the PSLV. As you can see, it has got on the bottom. You can see three, but there are six strap-ons, which are strap-on motors, which are there. And then in the center, there is a core which is 140 tons propellant. On top of that, in the brown thing, that is the second stage, which is liquid. On top of that, we have PSL written, that is the third stage. And on top of that, again, there's a liquid fourth stage. On top of that is the satellite. As we can see, this is 44 meters height and 2.8 meters is the diameter of the core. 320 ton lift and 51 broken. Now it is 52 launches which are successful. Actually 54 because 53, because there were two development flights also which were successful. GSLV configuration is, it has got four liquid strap mounts L40s, and the core solid GS1, which is the same as the PSLV. First is 140 tons. GS2 is again the same as PS2, that is the liquid engine, Vikas engine. On top of that is the cryogenic upper stage. With that, the height is 49 meters, lift of mass of 415 tons, and it can take is a 2,500 kilogram payload into a geosynchronous transfer orbit. This is a Mark III LVM3. This configuration is two S200 strap-on motors, which are very high performance, 200 tons propellant each. And then there's a liquid 110 kg liquid stage, followed by a cryogenic upper stage. It's a very short, nicely defined launch vehicle, and it has a base diameter of 4 meters, and it can carry a 4,000 kilogram payload into transfer orbit, 640 tons lift-off mass. This is, as I said, this is going to be used for the Gaganyaan. SSLV, I only have some ITIS representations. This is a three-stage all-solid motors, 34 meters, 2-meter diameter, and 120. It's a small vehicle only. And a unified launch vehicle, its basic configuration is two 200-ton strap-on motors and the semi-cryo core stage. Semi-cryo means it is cryogenic oxygen, liquid oxygen, and aviation kerosene, which is the propellant in this one, followed by two cryogenic engines above that. And this can be configured with 2, 4, or 6 strap-on rockets. Thereby, its capability can be increased from 4,000 kg to some 15,000 kg or something. Now, having talked of these various launch vehicles, we'll go to how the assemblies are prepared. The one very important factor which goes into the preparation of these sub-assemblies. See, I can talk about electronic sub-assembly, but I'm sure whatever I'm saying is relevant for other structural, chemicals, and propellants and mechanical assemblies also. For the electronic sub-assemblies, there is a screening process which starts right from the procurement of the basic components like resistances, capacitances, transistors, ICs, everything. And MIL standard 883 is the standard which is used for screening of all articles. This is the one standard which is used worldwide. Everybody uses these standards. And all electronic articles, they are screened before they are assembled on printed circuit boards. And the boards are tested once again after assembly, and conformal coating and all those things are done. After they are again tested to various levels of standards. And one very important test which is done in all of them is a thermal test, where for military standards they are taking from cycled between minus 40 degrees to plus 125 degrees Celsius. It is cycled the number of times over 1 week period, 168 hours. That is the military standard which is followed. When that ensures that all the components and all the circuit board which are prepared, which are bought and prepared, they are of a very good uh, quality standard. Of course, it is functionally. Of course, those circuits are tested and they are found to be okay. Only then they are used for further assembly processes. Now, the tests which are carried out on all the electronic, electromechanical sub-assemblies, functional tests, which I said just now. Generally, I'm talking about electromechanical assemblies, so the bias, scale vector, nonlinearity, frequency response of the functional circuits. Then there's a vibration test, which is done to find the resonant frequency of the assembly and its ruggedness. That is, when you do a vibration test, it should not things should not start coming out. Even nuts and bolts, they have to be rightly tightened and correctly positioned. Then the electromagnetic interference and compatibility test, EMI, EMC tests, because there are all sorts of assemblies, sub-assemblies which go into this launch vehicle, which radiate a lot of electromagnetic waves, and they'll be interfering with other circuits. So, in electromagnetic interference and compatibility tests are carried out. Then for satellite, there's thermovac test, where the completely assembled satellite is put in a huge thermal chamber, and it is made functional first of all, and it is put inside, and it is cycled between 0 and I think 70 degrees Celsius. And some more tests which are on software, which we'll come to in this presentation. So now we'll talk about softwares. Basically, I'm talking of flight software, which has to go through its life cycle of evaluation before it gets qualified. Now, generally, all softwares, whether they go for flight or for any other purpose, even the software which we use in various apps in the mobile phones and computers, it has to go through some qualities. It has to be properly structured and should be modular. This is the basic requirement for all softwares. If it's not properly structured, if it's not modular, it'll have some. Each modules will be interfering with other modules, and it will be a real mess if you have to correct it later on. It should be portable. Portable means it should be able to go from one platform to another. As we'll go through in the presentation, you will realize that the flight software has to be tested in a high level computer, as well as it has to run in the flight computers. So definitely that level of portability has to be there in the softwares. Should be maintainable. That is understood. We should be able to correct it as if and when required. Of course, you can't do any correction once it has been loaded into the flight's computers. But any maintainability has to be done before it's finally formed and put in the flight computers. Robustness, that we'll realize as we go through this. What is meant by robustness? Efficiency, obviously, we understand it should do its work in an efficient manner. Whatever is destined application, it should be able to do that. And additionally, for flight software, execution time has to be minimal. Okay, now we'll go through how it's done. It goes. So first is code inspection, mainly carried out manually to ensure compatibility with the design. See, what happens is that the application designers, like the people who write the control laws, navigation, guidance, autopilot, all those things, they are not computer. They can be, but they are generally experts in their own fields. So they make design, and the design is passed on to the computer designers, the software designers. So, so code inspection ensures that whatever is designed has been carried out correctly into the codes. Manually doesn't mean that somebody goes with a 500 pages of printout, goes home and pores over it. No, it is done on computers only. Basically, you look at the codes, see how they are executed. This is called stepping through the codes. You step through the code to see whether it's going doing properly, and when there are any flags are getting set. All those things are ensured during code inspection. Then a walkthrough. These code inspection walkthrough, they happen together, and then you do the code level execution in a simulated host environment. What it means is that you the flight computer is simulated in the high level computer, and its execution is studied in the high level computer. Why this is done is, if there are any dead codes or dead loops, and that codes means codes which do not get exercised during the execution of the flight software. And loops also same thing. Supposing somebody has created a loop and that is not getting exercised at all, so these things have to be removed, or they have to be studied and corrected, removed if required, because the least they do is they increase execution time. They may also interfere with the actual operation of the flight software. Then the next level is the simulation level. That is the you have the flight software and the simulated flight profile. Both are running in the same high level computer. What it means is that the simulated flight profile means that as the rocket goes up, launch vehicle goes up, it generates its accelerations and rates, and some other parameters also. So the simulate flight profile generates those outputs of the flight, and they are given as input to the flight software. The two of them run concurrently in the same high level computer. The two have to match with each other. Ultimately, this is a flight computer which is going to fly that launch vehicle. That launch vehicle is being simulated in the high level computer, and the flight software is also running. The two have to run together in synchronous and efficient manner, and and that is to see whether any bugs are there in this execution. And this is tested hundreds of times in under different flight profiles, under different conditions, just to ensure that whatever conditions that may exist, that may come in the flight scenario, the flight computer is going to handle all those things without any problem. So we run these multiple hundreds, or maybe something like 500 to 600 times it is run, and the the flight software should be able to run it nice properly. And this is what ensures the robustness of the word earlier which I was going to which I mentioned, robustness. Flight software's robustness shows that under all sorts of inputs, even undesirable inputs, the software doesn't fail. It is robust enough to to cater to all sorts of input, which right or wrong, what sort of any sort of input which can come to the flight software. It is able to handle all those things without causing any failure. Next is the execution of the flight software in the actual flight computer. Now, after this previous step is done in the high level computer, the flight software ready to be put in EPROMs and put in the flight computers. And so these tests involve the actual flight computers and other flight hardware. These tests are called hardware simulation test, HSTs. These are carried out at progressively increasing level of integration. Processors alone, it's not one processor which is like flying the launch vehicle. There are at least three: navigation, guidance and control, and there's a lower stage computer. So at least there are three computers which are in the loop at different times. So so there are processors alone are is one level of tests. Then processor navigation sensors systems and the processor control system. These three levels of tests are carried out uh, for evaluation of flight software. Now, hardware loop simulation. This is what I had defined. So, what happens here is there is a simulation computer in which the launch vehicle is simulated. So, as the flight takes off, it generates rates and accelerations which are given to the navigation system. The navigation output goes to guidance and digital autopilot, and that goes to the control electronics, and then that goes as the drive commands to the launch vehicle, simulated launch vehicle in that case. And so that's where the loop is closed. This is a closed loop test. So and so the whole profile is tested in this way. Data is taken through telemetry data acquisition system. So the first level is with just the guidance and DAP computers. Sorry, no, not like that. Now, what sort of tests are done over here? The nominal inputs are given to the profile. That is the simulation computer. It generates different type of flight profiles to be able to simulate different levels of launch vehicle activity. That is, the launch vehicle could be in the real life also. The launch vehicle could face a lot of disturbances. So all the disturbances simulated in the simulation computer and given to and the vehicle is supposed to respond to that, or rather give outputs to the navigation system based on that. So nominal inputs are given, which could be expected in flight. Then with inputs with added disturbances within 3 sigma dispersion limits, which may occur during flight. Then the next level of tests which are done is stress tests, where the inputs are not possible to occur at all. This could happen in case there is a failure. Some sort of failure occurs because of which the inputs just go haywire, and we just don't cannot imagine what sort of inputs. But are also simulated. The only reason for doing this test is that the flight computer shall not fail under any circumstance. It should not provide any undesirable commands to the satellite launch vehicle. And this is the real test to ensure the robustness of flight's computers and the flight software. Okay, so now once this is done, now we'll come to the aspect of um, launch vehicle integration. With this, what I ensure is that the electronics assemblies, navigation, guidance, computers, autopilot, control electronics, all those things are tested, evaluated, and made ready, and they are ready to be assembled in the launch vehicle. So now we come to the integration of the launch vehicle. So how this is done? Um, there are what you see over here is a tall structure, and there's a very small building which you see on the left side. So these things are this is the tall thing is called a vehicle integration uh, tower, which is called mobile service tower, MST, in which the whole vehicle is integrated. Then the small thing which you saw on the left side was the checkout terminal room (CTR), which is located very close to the MST. In this CTR, you have got all the power supplies and all the things which are required to uh, which will be required during integration of the sub-assemblies in the launch vehicle, and its testing while after getting integrated in the launch vehicle. So power supplies, function generators, multimeters, everything is available in this MST. And also the propellant loading is also done while the through the CTR. Another thing is that all these whatever equipments are there, they are all capable of being remotely programmed, because in the uh, final stages just before integration, nobody will be in the CTR. Everybody is going to be in the mission control center, from where all these things will be remotely programmed. Remote, all the activity will be done carried out remotely. Um, okay, so here you see there is a mobile service tower, which is I think which is around 75-meter tall structure, and a two-story building on the left side, which is the checkout terminal room. The link from the checkout terminal room to the mission control center is through fiber optic communication links. Okay, so this is the MST, the huge 75-meter tall structure, which has the umbilical tower on which launch vehicle gets integrated. It carries all the mechanical handling equipment. The various platform, that is the interesting part of it. It has different platforms. For each stage, there is a platform on which you people can stand and do stand or sit or put all the equipment, all the testing things, and carry out integration. Um and the top where the satellite is integrated, there is an ultra clean environment, totally enclosed, air conditioned, and dust free, absolutely dust free environment, because the satellite has to be kept in dust free condition. And after the vehicle is fully integrated, the MST rolled out 180 meters away, exposing the vehicle in the umbilical tower. You can see how it is done. In this one, you see that inside you see there are some strap-on motors which are already integrated, and the core stage is already assembled over there, and one strap-on is being hoisted up by the crane, and it will be ultimately connected to the basic launch vehicle. Um, then here you see the the PS1 nozzle end segment. The PS1 is 140 tons, and it is about 20 meters tall. So it is assembled in three uh, three segments. This is the NES, that nozzle end segment, which will be at the bottom. It will then there will be middle segment on top, and then the head end segment HES, which will be on on the top. So the three of them will be put together to form the first stage of the launch vehicle. This is the third stage of the launch vehicle, uh, which is you can see people are standing around. There's a very nice platform on which people are standing and carrying out all sort of activities, integration activities over here. Then this is the one other picture of the PSLV strap-on motor being hoisted to integrate with the first stage. You can see people are standing in between and guiding this stage up. Then this is the second stage, which is brought to the MST, which will be integrated on top of the PS1. This is the satellite. This is the fourth stage. On the bottom, you see the fourth stage, and on the top you see the satellite IRS-1, which is an old photograph, which is integrated with the fourth stage of PSLV, and that is going undergoing some tests. This is not on the mobile service tower. It is somewhere else in the lab only somewhere. Now this is the uh, completely integrated launch vehicle, which is, and you see this mobile service tower has been rolled away some 150 80 meters away, exposing the launch vehicle and the umbilical tower, which you can see behind the launch vehicle. There's another view of the same thing. You can see the mobile service, the launch tower on the launch pedestal on the right side of the launch vehicle. You'll see so many cables coming out come between these the launch vehicle and this tower. These are the umbilicals, and this tall thing is also called umbilical tower. So the umbilical tower carries all the lines for electrical power. Right? Still, the power for the launch vehicle is being supplied from this checkout terminal CTR and onwards to MCC. Now we'll look at the pre-launch operations. What happens is after complete assembly has taken place, uh, there's a launch rehearsal which is done, a fully detailed launch rehearsal um, right from the basic, from the like the full duration launch rehearsal is done, in which every step which is going to be taken during the launch is is rehearsed just to see um if there is any lacuna in any of these in the launch countdown. Vehicle, of course, is maintained in safe mode, um, so that actually even the stage ignition commands are also given. But since maintain vehicle is in safe condition, it is it doesn't ignite any stage. Propellant loading is also carried out. That is already the solid motor is already loaded, but the liquids have to be loaded. So that is tried out. It's not done. It's not completed, but just to see if there are any hang-ups in propellant loading, in liquid propellant loading. It's only after successful completion of the launch rehearsal that is final clearance is given for the actual launch. Now, pre-launch operation carried out. We start about 23 hours before launch. This I'm talking of PSLV. For GSLV, times will be different. About 23 hours countdown is there. It could be different by a few minutes or maybe half an hour or something. So initial operations are propellant loading into the liquid motors. This is carried out with extreme caution because the two liquids which are being loaded are extremely corrosive and reactive with each other. That monomethyl hydrazine and N2O4. N2O4, as you know, is oxidizer, and monomethyl hydrazine is the fuel. The two, if they come in contact, they will cause it. They will start burning. So they have to be separately loaded and kept safe. And obviously, nobody is allowed anywhere near this whole thing. So it is remotely programmed from the MCC through CTR into the MST and into the launch vehicle. Then after this is after all these activities are done about propellant loading, and of course in case of GSLV the additional thing is cryogenic loading, which is done just very close to the actual launch. Otherwise, these things are at minus 180 degrees Celsius. It will just vaporize. After this, the MST is wheeled out to that 180 meters distance, and the launch vehicle is exposed with the umbilical tower. And then the vehicle is ready for launch. In the final 15 to 20 minutes, all systems are made ready, operational, and power to the vehicle is switched from external, that coming from CTR, to internal, which comes from internal batteries. So with this, all connections from the ground are removed from the launch vehicle. Then all the countdown operations are carried out from the launch processing computer. There is no manual intervention which is permitted after this. After you go to launch processing computer, the launch processing computer, in those last 15-20 minutes, it its job is to not only to sequence the of all the operations but also monitor in a very detailed manner all the pressures and temperatures and voltages and everything. It is it is it is monitored, and it is expected to be in limits. The another job of the countdown is to all the telemetry stations, downrange stations, uh, to be kept in full readiness. And this is done during launch rehearsal also. During for example, for PSLV, there is a telemetry downlink station in Sriharikota. There's another one in Trivandrum, Vikram Sarabhai Space Center. There's a third one in Car Nicobar Islands. There's fourth one in Mauritius. So with these things, with these four stations, we are able to monitor the flight of uh, this uh, till satellite separation. And of course, when the 104 satellites were launched, there was a fifth station which was created in Antarctica. As you know, from between Kanyakumari southwards, there is no landmass at all on which um, we could position a downlink station. The next thing is in Antarctica only. So that is where a downlink station was created. It is still operational, of course. And a few seconds before launch, the umbilical cables are removed. It has to be by remote command because the MST is not has been removed. Nobody can climb the launch tower, the umbilical tower, to remove these. And anyway, the vehicle is in a very is fully armed and in a very, it's not a safe thing at all. So it has to be done completely remotely. Of course, one thing is which is there is that if there's some problem because of it, the umbilical has to be mated again, then it's a very long process. You have to bring that MST back. You have to put all the platforms, and then you have to mate all the things, do the correction, whatever is required to be done, and then roll the MST back, and then demate the umbilical screen. So that's going to be it has never happened during all the 60 odd launches which we have done so far. This is something which has never happened. And as the vehicle takes off, the last minute plugs they get detached by the momentum of the vehicle. Now post launch, what happens is after t equals 0, count goes upwards and continues till the final satellite separation takes place. All vehicle sequencing events, stage separation, ignition, heat shield separation, satellite separation, closed loop guidance initiation, all those things are time based on this count up clock. We must have seen the real time display of this uh, of the launch. The the data which you see on the plot boards, that, as I said just now, it is received in all the downlink stations and relayed to Sriharikota and brought to display. So actually, there is a 2 to 3 second delay between the generation of the data, its reception in the downlink stations, and relaying it to Sriharikota. Okay, I have already mentioned this, 2 to 2.5 seconds. Now we'll come to another aspect, that okay, all this launch has taken place, but how does the control actually takes place? What and how is the vehicle controlled? So the why is control required? I I wonder if some of you might have learned about control systems. Supposing you are driving a bike on a road, so how do you drive? You hold the steering wheel. You in the car steering wheel, in a bike it's on just the handle, and you control the steering wheel or the handle so that your vehicle remains stable. So control is required to provide steering commands to the vehicle, and to provide stability to the control commands. It's so once you have steered the vehicle, it's going ahead. Then you have to provide stability to the control commands. So this is why a control is required. How it is done? No, how is control carried out? There are various ways. Um, Why in the atmospheric phase, you can use the atmosphere to use aerodynamics to stabilize the vehicle by putting fins. Um, this was used in ASLE, but it has never been used afterwards. And in sounding rockets, use fins, but otherwise it has never been used. But during the powered phase of flight, that is, even though whether you are going through atmosphere or not, the vehicle thrust has to be deflected to carry out any control maneuver. See, there is no other way to control the vehicle except there is a flame which is coming downwards. You have to deflect the flame to carry out any control maneuver, because with that only you will be able to turn the vehicle or take it to a different direction. For the core, the base stage, what is done is the flame is coming out. An oxidizer fluid, strontium perchlorate, at very high speed is fed into the nozzle. You can see here. Uh, in this one, you can see the nozzle, and in the upper view, you see there are 24 vents around. So through these vents, the strontium perchlorate is ejected out, and that helps in deflecting the main thrust. That's called secondary injection thrust vector control. For the liquid engines, I don't have a photograph of that one. It's called Vikas engine. The Vikas is short Vikram Ambalal Sarabhai. Vikas engine is used for uh, for here. What happens is that engine itself is deflected in all the directions to provide the uh, required change in direction of the thrust. The thrust will come, the flame is coming through the nozzle. You deflect the nozzle so to deflect the vehicle. For cryogenic also a gimbal engine, but it is different from Vikas engine. Then during unpowered phase and in satellite applications, RCS, reaction control system, is used, where you have a stored gas, helium, normally at a very high pressure, something like 200 pounds per square, 200 psi, 200 atmosphere, sorry, and that is released through small vents to provide control. So this is how control is done in the different stages of the launch vehicle. But how do you sense? How do you know that whatever we have done is correct and sufficient? For this thing, we have got in the navigation system, which has got these electromechanical sensors and the software, which uh, tell you the present location. Then the guidance system, which will act on the present location, and it has got the final destination in it's stored in it, and it will define how to go from the present location to the destination. That is the guidance system. And the digital autopilot takes the guidance outputs and makes them suitable for this stage control systems. Then of course this is all computers, but then there is control electronics which will suit the DAP outputs to the for the requirement of each stage. We'll go to NGC first. NGC takes, as I was telling some time back, the vehicle in its movement, in its flight, it generates acceleration and rotation. So these acceleration and rotations are has to be sensed. They are the only outputs which are coming from the vehicle. So these outputs are to be sensed by the navigation system. Uh, okay, this is the total NGC scheme, where you can see the vehicle states, that the rates and acceleration are given as input to the navigation system. Uh, so from the rates and acceleration, it is expected to integrate the data and provide and generate velocities and attitude, and integrate again to get the current position. And then the guidance system has a preconceived knowledge of my destination, and it is supposed it will work on these two and provide the control outputs to the vehicle. This, in very short, is how the NGC functions. Navigation system senses the uses it has got gyroscopes and linear accelerometers, and so accelerometers sense the vehicle acceleration, and through double integration, it generates velocity and position. The rates are sensed by gyroscopes and integrated ones to provide vehicle attitude. That is the angular position. We have to respect the proper frame of reference by overlaying transformations and such things. Now, there's one very important thing which is carried out is called pre-launch alignment. So what happens is, in a general case, the black coordinate system is the vehicle axis, and the red one is the navigation system axis before you carry out the alignment. So after doing this pre-launch alignment, and that is required because the two have to coincide with each other. They have to become like this. So, so this is one intricate pre-launch uh, pre-launch activity which has to be carried out before the launch takes place. Now, how the vehicle control action takes place is like this. Once again, we see the launch vehicle. It's giving the kinematic output, the rates and acceleration to the sensors. Then delta theta and delta V is generated. Then navigation, guidance, autopilot, and control systems. They are this in this way the loop is closed. Now the guidance system is programmed to provide the most optimum path to reach the destination while fulfilling the restraints like minimum should consume minimum amount of fuel, avoid land masses like Sri Lanka. I was saying it has to be avoided. No excessive rates to be subjected to the vehicle. Vehicle has to be kept safe and keeping in mind the relevant stage control systems, the requirements of the stage control system. So this is how, and the guidance system effectiveness is judged by the amount of propellant which gets consumed and propellant which remains. This you can say is the block diagram for the guidance scheme. Uh, so this is how the guidance of the vehicle takes place. Control already we have seen. So this is how the navigation guidance and control system for the vehicle takes place. Now vehicle sequencing is another thing which is done, which is which starts from ignition of the stage first stage motor, which takes place on ground, and after that all the stage motors are commanded by the flight computer. There are two types of commands which are generated by the guidance system. One is commands which are fixed time commands. Second, the command which are based on the vehicle velocity and position and some other criteria. Like heat shield separation comes only after the vehicle is crossed 100 kilometers altitude, something like that. So guidance system generates all these commands. So okay, this is what I've talked about mission definition, the launch vehicle testing, integrational launch, and the NGC system. Thanks a lot for your attention and time. Thank you.